Well, this is pretty funny. We're in like lecture 14 of our statistics course, and you know what we haven't done yet? We haven't said, what do we mean by statistic? We haven't defined statistic yet. Well, we're going to do that today, of course, and we're going to look at, in particular, good sampling techniques, because statistics are based on samples, right? So maybe I'll kind of just put this here temporarily. A statistic is something that's based on a sample. You measure something about a sample, you come up with a number, you call it a statistic. I suppose you could come up with a color, you could come up with all kinds of things, but whatever. Something about your sample is a statistic. It's based on a sample, and it's supposed to be about an entire population. So you're pretty familiar with this, I'm sure. It's like, let's say we're interested in, what percentage of American voters are going to vote this way at the next election. Well, you can't call up every single one of them and ask them and compile a, you can't do it that way. So what you do is you say, well, let's get 1,000 of them. Let's just ask 1,000 of them, and we'll try to sample from around the population, get 1,000 of them, and we'll what percentage of those are going to vote this way, and we'll just assume that, yeah, that's true for the whole country. That is the essence of statistical sampling type stuff. So anyway, we're going to spend this lecture on this kind of stuff, and to get started, I'm going to have to first define 5 words for you. And I think I'll motivate these definitions with a little question here. What we'd like to know is, what is the percentage? What are the percentages, I guess, of X nuts, Y nuts, and Z nuts on this plate, let's say, on this table, whatever, on this plate. Okay, that's the question. Hey, look, there's X nuts, there's Y nuts, there's Z nuts. What's the percentage of X, Y, and Z nuts on this plate? Now, since this is a small enough plate, we can, in fact, count them all, and that's what we're going to do. So we can define a census, which is when you count every member of a population. Okay, time to define population. What do we mean by population? Well, in this case, what we mean is all the nuts on the plate. That's what we're really interested in, all the nuts on the plate. If you were trying to figure out the percentage of American voters that are going to vote a certain way, the population you're interested in is actually all of the American voters, or maybe all people that are likely to vote or something. That would be the population you're interested in. So usually you cannot take a census. We only do a census every 10 years, and it's not even super accurate. But in this case, we got a small enough population, we can do it. We're going to count them all. And so I'm going to count the X's. Get a different color to start doing my work here. So counting. And assuming I counted right, there are 15 X's, there are 17 Y's, and there are 12 Z's, which adds up to 44 altogether. So you might say, oh, the census is 44. It's like, no, the whole thing is a census. It's the idea of going to everything. The census, they ask you all kinds of questions, like, hey, how many brothers you got, whatever. So there's our information. Now, from this, we can start compiling our statistics, so to speak. So 15 over 44, if you turn that to a percent, it comes out to like 34.1%. And I'll just say etc. We don't have to calculate them all. Now, this is not a statistic. This is a parameter. And maybe I should put that in blue because it's another one of our big definitions here today. Whoa. Okay. Parameter. Why is it a parameter and not a statistics? Because we didn't actually take a sample, we took a census. So the parameter is a characteristic of the population taken from a census, I guess. Or it doesn't have to be if somehow we just know it for sure. I don't know how you do that without a census, but let's just say it this way. So that says, or we just know it exactly and for sure. So we know, how do we know? We did the count, right? We counted them all. We know for a fact that it's 34.1% X nuts. We know that. So we don't call that a statistic. We call that a sample. What did I just say? We call that a parameter. Thank you, stupid brain. Sounding like Biden here. Oh, sorry. Anyway, that's what a parameter means. Okay, so in a case where, let's kind of squeeze this over here. If population, see, I am losing it. Okay, let's hope I can stick with this. So if population is really large, much bigger than this plate, it's not practical to do a census, right? So we take a sample. I guess we could define sample. Sample. Usually small by comparison. So a small part of the population that we analyze. We analyze with intent of finding out about the population at large. Finding out about the population at large. So that's what the sample is. That's just the small part that you take. Now, if you want it to tell you something about the population at large, one hopes it is representative. Oh my goodness gracious. Never make a lecture on 5 hours of sleep. One hopes it is representative of the population at large. And that's a key idea. Whenever you sample, your goal is to have that sample be representative of the entire population, right? And then finally, we can get down here and define what a statistic is. And we've already mentioned this, so this should be no surprise. Statistics are compiled from samples. And you might say it this way, you want to be good with your definitions, are compiled from samples to try to get at parameters, right? Because the parameter is the absolute true value of whatever it is you're measuring, the absolute true value of percentage of x's, whatever, to get at parameters. So if I had only somehow reached in at random and tried to take like a random sample, and maybe I took those and I analyzed the percentages of x, y's, and z's, I bet you I wouldn't come out with exactly 34.1% x's, but I would, by hoping that it was a representative sample, let's say I got 20% x's, I'd be saying, yeah, I think it's about 20. Of course, I'd be way wrong because my sample would be too small in this case, but you get the idea. So this is what's going on out there. There's a population, we're interested. The population has certain parameters. We take a census if we can, because that would be the most accurate way to do it. But if we can't, we take a sample, and then when we compile our math and data and whatever, we can't call them parameters, so we call them statistics. The statistic is estimating something about the population. We're hoping it's accurate. Now, because when you're sampling, you're kind of blind to the whole population, right? You're kind of, I don't know, mixing things up and hoping that you're getting some good sample of soup or whatever there, but there's going to be some error. It's not going to come out like, for example, well, actually here, right here, let's look at this example right here. So it says consider an aquarium. The aquarium has, it's a big aquarium, has 500 trout, okay, and 500 other fish. So notice it's half trout. That's a parameter because we know this for sure. It's 50% trout. Okay, we know that. Usually with statistics, you don't know that. That's why you do statistics, because you don't know that. You need an estimate. Okay, so it says right here, pretend we don't know that. Okay, so try to determine the percentage of fish that are trout. Hey, what percentage of fish are trout in this tank? I don't know. I kind of forgot. It's like, okay, well, then just take a sample. And let's say, for some reason, we chose 20 as our sample size. In a sample of 20, here's a question for you. Since it's half trout, do we really expect? Do you really expect 10 trout? That's what the 50% would predict, right? Hey, I got 20 trout here. They're 20 fish here, and they're supposed to be half trout, so I guess I got 10 trout. But are you really going to get 10 trout? Maybe. Every single time? I doubt it. So that's the problem, right? So since your sample is random, you're sampling at random, have some random error. You'll get 10 on one sample, then 9 on another sample, then maybe 10 again, and then maybe 8, and then maybe 11, whatever. It's going to bounce up and down a little bit. So there's a little bit of error. There's a little bit of bounce in your sample. And if there's a little bit of bounce in your sample, then to base it on any one sample, like let's say I use that sample. Oh, it was 9, so it's 45% trout. Yeah, that's it. You have a little bit of error, and that's called sampling error. It's the error that's just due to the fact that you're taking random samples, and there's nothing you can do about that. So let's maybe put this in I'm going to write this all official, like I'm going to say random samples are, by definition, subject to random fluctuations, right? Sometimes you'll get 10, sometimes you'll get 9, sometimes you get 12, whatever. So any statistics you compile are going to be close to correct, usually. You don't even know, right? Everything's probability. Nothing's ever guaranteed. But so any statistics you compile are usually going to be close. But with some random amount of sampling error. Okay, so the sampling error is kind of not your fault. You can do things to try to, minimize sampling error. Like, first thing that comes to mind, take a bigger sample. If you sample 2, you're going to have some error there. If you sample 18,000, you're not going to have as much error, most likely. Take bigger samples helps. That's probably the main thing you can do. Take repeated samples. Try it again, try it again, try it again. This is often done with people who do experiments, and they try to measure things, and they say, well, let's see if these other guys over here in a completely different state can repeat the experiment and get the same result. That would give you a little more confidence that they were right? So you could take repeated samples. I'll put in etc. We'll learn some more things later. So sampling error is going to be an inherent problem. It's always going to be with you, or there's always going to be error. You cannot say that because my sample says this, therefore it's right. You can't do that. You can never do that. You can put a confidence interval on it maybe, but okay, so now let's get to some actual sampling methods. We want to learn some of the methods that are used or can be used, and maybe they should be used, and maybe they shouldn't be used, and stuff like that. So if you go a sampling, you want to be aware of this information. So here's an interesting thing. We got a math classroom, and we got 24 students in this math classroom. So these 6 students are all sitting in one row, or column, I guess, and then these are all in another column and another column and another column. So we got 6, 6, 6, and 6. We got 24 students. Now, we wish to randomly sample 6 students to take an intense math interview. Intense, which means we don't want to do it too many times. So we're going to sample 6 students. How should we determine our sample? Okay, we could, one way to do it is just say, I feel like taking the sample now. I'm just going to go down to the Commons and see if I can find any math students down there, and I can ask them. Okay, you know what that's called? That's called convenience sampling. because it's convenient to you. You're not trying to be scientific at all. You're just saying, hey, I need some students. I'm going to go try to find some students. Oh, there's some students. Hey, we're good. And so I'll just say right away, convenience sampling, always questionable. By which I should say the results are always questionable. Why are they questionable? How in the world can you guarantee your sample is representative? You go down to the commons or whatever, you see 6 math students all sitting at the same table. What if it's the 6 students that really hate math? You know, the 6 math haters, and that's why they hang around together. Or maybe it's the 6 math freaks. They love math, and that's why they hang around together eating lunch or whatever. You know, you don't know that your sample is going to be representative of the entire classroom. The population of interest here would be the classroom, I suppose, unless it's more than that. But let's just say it's the classroom. Those 6 students down at the lounge or whatever, they may not represent your entire class. Okay. So here's another thing we might try instead. We wait until class is in session, everybody's present, and then we ask for volunteers. Hey, who wants to take a math interview, an intense one? Who wants to do it? And then 6 people raise their hands and go, yay, me, I'll do it. Okay, this is called a self-selected guinea blue. These are, actually there's 2 words I've heard for this. Self-selected, or another way of saying it, pardon me, is voluntary response. It's the same thing. You're either selecting yourself saying, hey, I'd like to be part of the sample, or you're just volunteering. Hey, I'd like to be part of the sample. You know, in both cases, it's the same. Hey, I'd like to be part of the sample. So self-selected or voluntary response, again, results are always questionable. And the basic problem here, again, is how can you guarantee that the 6 eager people who would really love to give you their opinion are representative of the whole class, right? You get the most, and I don't even want to say eager because they like math. It's just eager because they got something to say. You get the most eager respondents, those with strong opinions. That'd be a good way to say it. That'd be a good way of saying it. Those who have strong opinions they want to share. And you don't necessarily want to do that. If you're trying to gauge what's the climate or whatever of the entire class, you want to get a good mix of some that have strong opinions, some that go meh. You know, you want to get a mix that represents the entire class. So asking, hey, who's going to volunteer is not a good way to get a representative mix. Okay, so don't do that, is what I'm trying to say. Don't just say, hey, who wants to fill out a questionnaire? That's not a good way to take a sample. Don't just say, hey, who's around? That's not a good way to take a sample. Okay, this one. In fact, I'm going to cross off part of this. It says, how about we list everybody in alphabetical order? Well, that's not even necessary. Let's just say that we go down each row or whatever. It says, here's the key part here. Interview every 3rd person. So maybe we go, hey, Abby. Let's see, 1, 2. Who would be next? Seamus? Biff? You know, something like this. We go down and we just, every 3rd person, we just grab them and say, okay, you're up. Give me the interview, will you? I guess that would get you 8 students, not 6, but whatever. So if you did that, that would be called systematic sampling because, well, doesn't it sound so systematic? You're like, hey, every 3rd one. So you might say, I'm kind of blinding myself to who I'm getting, right? They're not volunteering. It's not like I'm just doing it by convenience. I am being systematic about it. And I'm not going to say it's always bad, but I am going to say can produce misleading results. And so it's not ideal to do it this way either. Can produce misleading results. And there used to be something I could do in a math class with graphing calculators that made this point really, really well. You could enter a graph of y equals sine of, you know, some number x or whatever, and then you could set your graphing window to a whatever, and then you would get a little sine wave. That's what a sine wave looks like. And then you would realize that, no, that's completely wrong. It's completely wrong. And the reason is because the real sine wave might look something like, you know, something like this, but the calculator it only has like finite pixels that it can draw, right? So it says, okay, I'm going to evaluate here and draw at this pixel. I'm going to evaluate here and draw at this pixel. Then I'm going to draw You know, this picks, and you can see that you're not getting the right wave when it connects those. See what I mean? So systematic sampling can also give you misleading results, so you kind of want to stay away from that too. So these might be your favorite ways. Go down to the commons, just ask for volunteers, just take every fifth one. But those are not really good ways to do it. Here's another way, and this was done in the early 20th century. There's this really famous example of a poll that went really wrong. Did you ever see Dewey Defeats Truman? Did you ever see that newspaper, Dewey Defeats Truman? By the way, Dewey did not defeat Truman. Truman won the presidency. But this newspaper was so confident in their poll that Dewey was going to win that they started printing all these papers, and the next thing you know, they had to throw them all out because, no, Dewey did not defeat Truman. So what went wrong? They did this kind of a thing. Not exactly like this, but this kind of a thing. So let's say in this case, the class that we're interested in has half boys and half girls. So, well, we want 6, right? So just get a student worker and say, hey, look, just grab 3 girls and 3 boys, and then we'll have we'll have an equal number of boys and girls just like in the class, and that'll be pretty good. This is called quota sampling. The idea being that you gave the student worker a quota. Go get 3 of these and 3 of those. And that's what they did in the, I forget what the name of the paper was, the something something Tribune. That's what they did. They said, hey, we're going to get so many people here and so many people there and whatever. But the problem is the people that were given the quotas, they would resort back to convenience sampling. So if it's like, hey, I want you to get 4 20-year-old, 14 20-year-old men in their 20s, put it that way. 4 men in their 20s, and ask them, and what they do is they just walk down the street, take the first 4 men they found. And so it wasn't representative of the whole population. So I'm going to say not so good. And Dewey Defeats Truman is all the proof you need. Okay, actually the magazine went out of business. Okay, how about this then? The class is half boys and half girls, so we randomly select 3 names from the list of boys and 3 names from the list of girls. Okay, this is getting good enough that it's actually it's done. This has a name. It's called stratified sampling. Now, what makes it acceptable is the randomly. We're going to randomly select 3 names from the list of boys and the list of girls. So there's a random element to it. Now, it's kind of like quota, get 3 boys and get 3 girls, but the reason is because, well, it is 50% boys and it is 50% girls. So it would be nice if our sample was also half boys and half girls. And so it's kind of like, they call it stratified because think in terms of cutting the class into 2 layers, right? There's the boys layer and there's the girls layer. And then from within each, you just randomly sample. And so what you end up with is, you end up with a pretty good sample. So it's break population into categories would be your procedure. Whatever you think matters. If the difference between men and women matter, then you should probably have, according to the, if it's 60% women, then 60% of your sample should be women and stuff like that. So break population into categories, which are called strata, which means layer. Then randomly, and that's the thing, randomly sample within each strata or category. That is the idea. This is done. So it's kind of acceptable to do it that way. Okay, we'll just say that since it's done, we don't have to argue much about it, right? Here's a different approach that is also used, and it's a little bit different. Instead of saying, okay, so many boys and so many girls, let's select randomly from the boys, and then we'll select randomly from the girls, what we'll do is we'll randomly select a row. In other words, up here, looking at this thing. Maybe we'll just randomly select this row, something like that. Or maybe we'll even randomly select 2 rows. So that's where the random element comes in. We're randomly selecting a row. Where am I? But then you're doing everybody in the row. So you don't randomly select from the row. You've randomly selected the row, but then you grab everybody that's in the row. So this has a different name. This is called cluster sampling, because what you're doing is you're sampling some clusters. Cluster sampling. Cluster sampling. So it goes like, it's kind of the opposite of stratified. Break population into clusters. And it's almost like geographic clusters, but I guess it doesn't have to be. Into clusters, randomly choose a few clusters. I don't know how many, but I'll just say some clusters. Sample all that are in those clusters. So these two, the stratified and the cluster, a lot of people have a hard time keeping these straight. So I guess with stratified, I'm thinking right away of strata, layers, and what you want to do is you want to sample within the layer, almost like a geologist might do that. They sample within this layer, see what kind of bones they get, and then they sample within this layer, see what kind of bones they get, something like that. Whereas a cluster is you're going to grab a whole cluster and you're going to sample everyone in the cluster, but the clusters themselves are being, something like, oh, here's not a bad example. Let's say you had like a bunch of city blocks. Let's just call those city blocks. So we've got 1, 2, 3, 4, 5, 6, 7, 8 city blocks, and we randomly select 3 of them. That one, and maybe that one. That was random. And so what we got to do is we got to go to every single house on that block, and every single house on that block, and every single house on that block. So that's something that's done, because you can see there's a convenience element to it. You send your dudes out, your workers, whatever you want to call them, your surveyors, your pollsters, that's what it is, out to everybody on that block, hit every single house. Okay. You hit everybody on this house, on this block. Okay. You hit every house on this block. Okay, fine. Instead of, okay, go here, and then go here, and then go here, and then go here, which would be like totally random, right? So anyway, cluster sampling is kind of convenient, but there is a random element in it, so it is used. Actually, a lot of times with these nationwide polls, they tend to do a combination of the two. So they might take a clusters of counties in a state, and then they'll do stratified within the county or something like that. Okay. Now, is this our last? Yes. Here's our last method. You ready? And this one is the very, very, very best. Hey, put all their names in a hat, mix them up really, really good, and then blindly, randomly draw 6. This is what we call simple random sampling. Not just random, simple random sampling. It's kind of as simple as you can get if you think about it. Every single, what do you want to say? You've broken it up into every single possible cluster, clusters of one, so to speak. Simple random sampling. This is the ideal. In fact, it's so ideal, I'm going to use a different color. Not that color. That color. It's ideal. Not only does every member of the population have an equal chance of being chosen for the sample, which is what random means, and that's what random meant up here. I mean, before you choose those city blocks, everybody here has theoretically an equal chance of being chosen, because you don't know which city blocks are going to be chosen, right? And then here, before you break it up into strata, every member of the population has an equal chance of being chosen. You're going to break it into strata, and then you're going to be randomly sampling within the strata. So there's random elements are telling you that every member of the population has an equal chance of being chosen. But when you put all their names in a hat, right, what happens is every possible sample can be chosen. Not only does every member, but every possible sample of a given size, of course, every possible sample of any given size has an equal chance of being chosen. So in other words, if I sampled these 6, it's random, there's a random, but it's not simple random, because there's other samples of 6 that are being missed by this method. Like there might be a sample where all 6 come from over here. That's not possible anymore. That sample is not possible with stratified. Or let's say every member of the population had an equal chance of being chosen here, but here's a sample of, let's just say 6. Here's a sample of 6. But we'll never ever going to get this particular sample of 6, right? It's not going to happen because it can't happen because we have to, once we've chosen the clusters, we have to choose from here. So that's what makes simple random simple. Not only does every member of the population have an equal chance of being chosen, but every possible sample of any given size has an equal chance of being chosen. Just think in terms of everybody in the hat. We're going to mix all of you up. We're not breaking you up into clusters. We're not breaking you up into strata. We're not breaking you up into nothing. Nobody's broken up into any kind of group. You just don't do it. You just completely, randomly select from the entire thing. Now, that's kind of hard to do in a country, right? Okay, you have to go way over to Montana, this county, this street, and find that guy. All right, you got to go all the way over to Connecticut, this county, this town, this street, find this person, whatever. It's hard. So they say, look, we're going to do this county in Montana and this county in Connecticut, and you guys go take stratified samples in those counties and whatever. That's how we tend to do it, really. Or not we, I don't do it. But that's how it tends to be done. So anyway, that's our sampling methods. So there's a few words to learn here, a few methods to learn here. And again, if you're ever going to take a sample, try to keep in mind, convenience sampling, no good. A lot of people do it, a lot of people shouldn't. Self-selected or voluntary, boy, is this done a lot. Hey, you got an opinion? Call in now and let us know. It's like, those are not going to give you good results. Systematic, no. Quota sampling, no, because the convenience element slips into there too. Stratified? Cluster? Okay, this is better. This is better. Simple random? This is the gold standard. This is the best way to sample. If you can do it this way, do it this way. If you must do stratified or cluster, then you must do... The advantage of stratified or cluster is you might be able to get away with smaller samples that are still representative of the whole population. Simple random sampling, if you happen to get, 15 20-year-olds in a row or something, you're going to have to take a much larger sample to try to even that out. So the moral of the story, I took this quote from a statistics book I used to do. If not collected in an appropriate way, the data may be so utterly useless that no amount of statistical torturing can salvage it. Okay, keep that in mind. Not all statistics is good statistics. Oh, look, we're at the end. Ha! Look at that, we're at the end. Cool. I knew I had more to talk about, but you know what? That's in the next lecture. Okay, see you in the next lecture.